Assalamu alaikum. Hi everyone.
Assalamu alaikum, sir.
Walaikum assalam rahmatullah. I hope you are fine.
Assalamu alaikum.
Walaikum assalam rahmatullah. So have you gone through the assignment yet? Have you started it or not? Anyone? Okay. Not yet. No problem. We still have time. But it's better to start as early as possible because we just discussed the topic. So the discussion should be fresh in your mind. So if you start now, it should be helpful for you, the lecture. Otherwise, we'll be going through different topics later on, and probably you might forget whatever was discussed earlier. Okay, so let's continue with the modeling that we started earlier in the previous class. So in the last class, we actually went through this calculation of inductance steps. And basically this inductance was seen from the stator side. So one set of inductance was the stator self-inductance. That is between the different sets of coils present in the stator circuit, like coil A and B and C and C and A. So that was basically the mutual inductance for the stator, whereas the self-inductance for the stator was denoted by LAA for the coil A, LBB for the coil B, and LCC for the coil C. Similarly, we also calculated the expressions or found the expressions for the rotor to stator mutual inductance as well as the rotor to rotor inductances. So in total, we came up with 4 different matrices. One was LSS, another one was LSR, that is the stator to rotor mutual inductance, and there was another one LRS, but we said that, well, LSR and LRS, the elements should be same. So because it is either you are looking from the stator circuit into the rotor circuit, or you are looking from the rotor circuit into the stator circuit. So the dimension for LSR was 4/3. However, the dimension for LRS should be different than LSR, but the elements should be the same. So you can simply say that LSR should be the transpose of LRS. Okay. So if you take the transpose of this, so you will get the required matrix LRS. So if this is 4/3, which we derived in the last class, this LRS itself should be 3/4. Okay, so well, it is seen that it is 3/4. So okay, so let's make it 3/4 because it's 3 rows and 4 columns for LSR. So this one should be 4/3, just the transpose. So once we are done with all these, we ended the previous lecture with this matrix, which is LRR, and we found that there are some 0 entries in the LRR matrix. What was the reason for that? The 0 entries here, can anyone recall?
So direct axis and quadrature axis are 90 degrees.
Yeah, so they are situated physically, they are situated or they are apart by 90 degrees. So there will be no mutual coupling between them. That's why the mutual inductances for, let's say, this should be, or this could be written as LFD1Q. That means you are trying to link up or trying to find out the mutual inductance between a D axis coil and a Q axis coil. So because they are 90 degrees apart, so that's why all those entries should be zeros. Okay. So remember, while we discussed this thing, okay, while we discussed the location of D axis and Q axis at the very beginning of the lecture, we said that we are actually assuming 2 axes. We introduced 2 axes other than the stated 3 axes. Okay, so the stated 3 axes are A axis, B axis, and C axis, and along with those 3 axes, we also introduced 2 more axes. Okay, One was going through the center of the rotor axis, okay, or it was actually following the main field direction. That was the direct axis or D axis. And then we said we are also assuming another axis, which is known as the Q axis, and their space difference between them, or the space difference between them, was assumed to be 90 degrees. So at that point, probably it was not that much clear why it was 90 degrees. Okay, why are we taking it to be 90 degrees? Why not any other degrees? So when we come at this point of calculation, specifically at this point of calculation, we find that, so you can see, because of assumption of this 90 degree between the rotor circuit coils, that is the D axis coils and the Q axis coils, we are actually having some zero entries in our calculation. So is it beneficial or problematic? What do you think? If you have some zero entries, should it be handy for us or should be not handy for us?
It would be beneficial for us.
It should be beneficial for us. So assumption of 90 degree was actually done so that we can have some additional advantage while we try to calculate these metrics. Okay. So because of this zero, what will happen? Let us go back and let us try to look at this. Okay. So if you look at this matrix representation, this flux linkage equation, that is equation number 4. So you can clearly see that, well, because of the presence of these zeros, there is no coupling between these currents, I1Q, and the D axis flux linkage. So actually that helps to reduce your calculation complexity. Okay. On the other hand, if there were some non-zero elements, okay, any non-zero elements there other than 0, then there should be some link up between these lambda FD and 1Q, and there should be some other link up between this lambda FD and I2Q, right? So by having a 90 degree space difference between the D axis and Q axis, we are getting this additional advantage. So this is the advantage of assuming that the D axis and Q axis are 90 degree aligned, okay, or 90 degree away from each other, so that we have some additional advantage while we try to calculate these metrics. Okay, so with the mentioning of this advantage, let's move forward. So whatever we have derived till now, let's try to go through some comments based on the derivation or based on the findings that we have till now. So number one observation is that, so whatever observation, so whatever model that we have developed for the synchronous machine, actually we till now what we have done, we have calculated the inductance matrices. And we have seen, we can see that clearly that these matrices LSS, LRS, and LSR, okay, other than LRR, they contain some time varying or position dependent quantities. Like what? If we go back, look at LSS, okay? Remember these three, LSS, LSR, and LRS, but not LRR. LRR is not time varying or position dependent. So you can see LRR, there is no theta appearing over there, okay? There is no theta, no function of theta is appearing there in this matrix. So LRR is not actually position dependent or time dependent. Whereas if we look at LSR, you can see the presence of theta s, okay? You can see the presence of theta s. And it is a nonlinear function. Cosine of theta s, it's a nonlinear function. Sine of theta s, it's a nonlinear function. Similarly, if you look at LSS, this is LSS, equation number 5. So you can clearly see it is cosine of twice of theta s, cosine of twice of theta s minus some fixed angles. Again, this is nonlinear cosine function, okay? All are nonlinear cosine functions. So in summary, we can say that even in the steady state, remember what was theta s? What was theta s? Theta s, what was the reference point for theta s? Was theta s measured from stationary frame or moving frame or rotating frame? According to this diagram, can you recall?
Stationary frame.
Yeah, theta s was measured with respect to some stationary frame, theta s or theta m, whatever. Theta is represented, it is the theta angle measured with respect to some stationary frame. S stands for stationary. So that means even in the steady state operation, even when this rotor circuit, even when this rotor is moving at synchronous speed, omega s, that is the steady state operation. Okay, it is moving at synchronous speed. There is no dynamics. Omega s is not anything other than the synchronous speed. So if that is the case, even under steady state, what happens to theta s? Is it fixed or changing?
It will change, sir.
It will change because it has been measured from a fixed frame. Okay, so even though this rotor has been rotated by the help of the prime mover, okay, by the help of the prime mover, even though you are rotating it at a constant speed omega s, even then this theta s is changing with respect to time. As time is changing, the rotor is moving with respect to time. So the position of theta, position of the d axis with respect to a axis is continuously changing even under steady state. So that means your inductance matrices will be time dependent. Do you get the point? Why is it time dependent or position dependent? The first line. Even in the steady
Yes, sir.
state, even in the steady state, that is a very important point to remember. Even under steady state, the inductances will remain time varying. Okay, that is a problematic issue. That is a problematic issue. To deal with time varying matrices itself is a problem. So this is one of the problems that we identify that lies with our already developed model. Okay, whatever we have developed, that means whatever inductance calculations we are done with, that those are time varying even under steady state. That is the problem. So even under steady state, theta s is changing, so L values are time dependent. So to get rid of that, what we can do, if we can transform these time dependent system at point number one, if we can get rid of the time dependency and get another representation of these matrices which would be time independent, then that would be beneficial for us. Okay, just a minute, I just have to attend a call, just a minute. So let's resume. So our target is to get rid of this time dependency. Okay, so if we can get rid of this time dependency, at least in steady state, that is our target. So for doing that, in today's lecture, we will be going through some sort of transformation. Okay, that transformation will help us to transform this time dependent or position dependent inductance matrices into time independent matrices, at least in the steady state condition. Okay. However, in the dynamic state, of course, the matrices will be changing. The inductance values will be dynamic. Okay, but at least in the steady state, we get rid of those cosine terms: cosine theta minus 120, sine theta minus 120, sine theta plus 120. All those things will no more be there. Okay, so that is our target. And for doing that, the transformation that we will be following is the Parkes transformation. Okay, and that was proposed by some scientist whose last name was Park, and that was actually proposed in 1929. A very historical thing. Okay, so the scientist Park, he introduced this concept of transforming or introducing some sort of transformation to get rid of this time dependency and get the matrices LSS, LSR, and LRS to represent them in terms of time independent parameters or time independent representation. So we will take a look now at the Parkes transformation matrix. So like any other transformation, as we can say the Laplace transformation, inverse Laplace transformation, or Fourier transformation, inverse Fourier. Similarly, in case of Parkes transformation, we also have an inverse associated with the Parkes matrix or Parkes transformation matrix. Okay. So now let us see how to do that or how to apply that. So in the parts transformation matrix, what we will do, okay, in reality, what we will do, this slide is only mathematics, okay? This doesn't tell us anything about the background of the calculation. For understanding the background of the calculation, let us take some of the notations first. So the parts transformation will allow you to move from the ABC frame, okay, to move from the three-phase ABC frame to a new coordinate system where you have D, Q, and 0 axis, okay? So you are in the ABC frame means you have the three-phase quantities, balanced three-phase quantities, let's say phase A, phase B, and phase C. And then using the parts transformation, you can go into a different domain or different coordinate system where you will have the D axis, Q axis, and 0 axis, or D axis quantities, Q axis quantities, and 0 axis quantities. This is the transformation matrix, 3 by 3, okay? And we call it TDQ0. Sometimes in some of the books, you might also find it that, okay, you are in the ABC and you are trying to go to DQ0, something like that. And the inverse part will be you are in the DQ0 and you are trying to go to the ABC frame. So this is Parks, this is inverse Parks. And some notation, some books, they follow this notation. However, we are only following this one, okay? And it should be understood that when we say TDQ0, that means the quantities are in ABC and you are trying to get the quantities in DQ0 frame. So again, the transformation matrix itself, the parts transformation matrix itself contains some cosine function of angles, some sine function of angles, and some other parameters which are constants, some K1 and some K2's entries. Okay, so there are some comments on the values for K1 and K2, which we will also discuss in this lecture. For the time being, we will take, in our derivation part, we will take K1 equals to 2 by 3. So in this K1 value, we will take it as 2 by 3, and K2 values should be taken as half, 1/2. What is the outcome of this? If we choose this combination of K1 and K2, this will lead us to this beneficial conclusion. What is that? The conclusion is that if you are in the ABC frame, whatever peak value of the ABC variable you will have, the peak values of the ABC reference frame and the peak value of the DQ reference frame, they would be equal. Okay, if you follow this, K1 equals to 2 by 3 and K2 equals to half, we will show the calculation detail. Okay, no problem, nothing to worry. We'll show it in today's lecture. So there is another choice for K1 and K2, which leads to another benefit. Okay, we'll also discuss that. So to start with, we will take K1 equals to 2 by 3 and K2 equals to half, and this is your ABC to DQ0 transformation, and this is the inverse transformation. So this is a 3 by 3 matrix, and once you understand this, then you can easily calculate this even by hand. Okay, 3 by 3 matrix up to 3 by 3, it's pretty easy to calculate the inverse of the 3 by 3. Now let us see how actually these are done in practice, or what is the background concept for this transformation. So remember, using the parts transformation, we are converting the ABC reference frame variables to DQ0 reference frame variables. So how does that look like inside a machine? Let's see. What we are actually doing using the parts transformation, let us see. So let's go back. We can also do it here. Yeah, we can also do it here. So, so you have the ABC reference frame. Okay, so this is your ABC reference frame variables. Let's say this is your frame A variable, this is your frame B variable, and this is your phase frame B or phase C variable. Combinedly, they give you the ABC reference frame. Okay, so any variable aligned along these three axes, be it the current or the flux linkage or the voltage or any three-phase quantities, that can be treated as the ABC reference frame variables. Okay. So what we are trying to do using the Parkes transformation, we are trying to move into the DQ and 0. Remember, these ABCs here, in this case, they are balanced 120 degree apart from each other. So that means it is a balanced 120 degree apart. It's a balanced system. So while we use the Parkes transformation, what we actually do, we try to find out the projections of the A phase quantity. We try to find out the projection of A phase quantity from the A axis into the D axis, from the B axis into the D axis, and from the C axis again into the D axis. So while you do that, you will see that, well, this is your actually Parkes transformation. When you find out these projections from A axis into the D axis, B axis into the D axis, and again from C axis into the D axis, that will give you the Parkes transform variable into the DQ, into the D frame. Okay, the D part is done because you are getting the projections along the D axis. Similarly, for finding out the Q axis representation, you take the projections from the A axis into the Q axis, from the B axis into the Q axis, and from the C axis into the Q axis. And you simply get the representation for the Q axis. So DQ is done. What about 0 axis? If you have taken the course on power system fault analysis, I hope you have already taken this in any of your earlier power system courses. So in the fault analysis, there are two kinds of faults that were analyzed, right? One was balanced fault. What was another one? Unbalanced fault. Balanced fault, the analysis of balanced fault is pretty straightforward. But what we actually did for unbalanced fault analysis, do you remember? How did we proceed with the solution for unbalanced faulted network, like line to line fault or line to ground fault, single line to ground fault, double line to ground fault? Can anyone recall? There was a concept named as the symmetrical components. Remember? None of you? Did you take this topic in your undergrad? Hello?
Yes, sir.
Okay. So what was symmetrical components? There was positive sequence component, remember?
Yes, sir.
Positive sequence network, negative sequence network. What was the other one?
So zero sequence.
Zero sequence networks. Excellent. So these zero sequence and these negative sequence, they were only present for unbalanced fault analysis, right? For the unbalanced case. For the balanced case, actually the positive sequence network and the balanced phase, fault analysis are actually the same, okay? Where you have the presence of the source. If you're trying to represent the positive sequence network for a generator under fault, in that case, for the positive sequence network, you introduce the generating source. Whereas for the negative sequence network, you don't actually, you just get rid of the source part and the remaining part remains same, looks same. The zero sequence network is only present actually for unbalanced network. But for the balanced system, there is no zero sequence component. There is no zero sequence component. Similarly, although we call it DQ0 transformation from ABC frame to DQ0 frame, but because we are assuming that throughout our analysis, we are assuming that our system under consideration is a balanced one. So actually the zero will not occur, okay? So we will not see the zero axis anywhere in our calculation further, okay? But the generalized representation is you are trying to get the DQ0 representation from the ABC representation. So now can you tell, now the next important question comes. So we are saying, or we are claiming that, well, we were in the ABC frame. So if we are in the ABC frame, that is a stationary frame. So theta s is creating problem because theta s is appearing inside this matrix. You can see LSR matrix. It is appearing as a function of cosine or a function of sine, etc., etc. So that's a nonlinear term. That is a position dependent term. All are problematic. To get rid of the problem, what we said, well, or Mr. Park, he said that, well, you can take help of my transformation and then you can go to the DQ0 frame, which will get rid of all this theta dependency. Can you tell why this happens? Just from whatever knowledge you have gained from the previous lectures. If we go from ABC stationary frame to the DQ0 frame, why is our claim a valid one? Why is it a valid claim? Can anyone tell? Remember, this dependency will not be there in the steady state condition, right? In the steady state condition. So do you remember that we introduced a rotating reference frame in one of our lectures while we tried to derive the swing equation in the first week's lecture? We introduced the we introduced the concept of delta alongside this theta. Okay, what was delta? Delta was the rotor position with respect to some rotating reference frame. Okay, with respect to some rotating reference frame. So this DQ0 frame, this d-axis, it is actually, we can say it is attached to the rotor itself, right? So wherever the rotor will go, the d-axis will move along with that. And q-axis is always 90 degrees apart from d-axis. So if we are calculating all the quantities with respect to d-axis and q-axis, then the benefit that we are getting, that the d-axis and q-axis themselves, they are also rotating at synchronous speed, isn't it? Because the rotor itself is rotating at synchronous speed. So what should be the speed of the d-axis and q-axis?
They will also run as.
They should be also moving at omega s. So that means if you can take all the variables that were along a axis, b axis, or c axis, because those axes were stationary, that's why theta s was changing even in steady state with respect to time. But if you can take the projection of these three axes along d axis and q axis, then the benefit that you get, as long as your rotor is moving at synchronous speed, they are constant. Okay, the projections that you get, they will remain constant. They are not a function of theta anymore. Okay, so this is the benefit that we are going to see, that even through calculation, we will be getting this benefit. So with this physical insight into the parts transformation, let's now go into the calculation part and the mathematics part. So we will be taking today some examples, some application, looking into some examples of the parts transformation, like three-phase voltages in ABC frame, how we get the DQ0 representation of the three-phase voltage, three-phase currents, and three-phase flux linkages, and etc., etc. Okay, let us see. So with this parts transformation, inverse parts transformation, and with these values of K1 and K2, we are expected this benefit. Okay, we expect to have equal values for the time independent IDQ variable. You see, we are not writing the 0 anymore. Okay, we are not writing the IDQ 0 anymore. We're simply writing IDQ, because for a balanced system, the 0 component will be non-existing. So the benefit is expected that the IDQ peak value, IDQ peak value, and IBC peak value should be the same. Another benefit, that with the introduction of this ABC to DQ0 transformation, we will get rid of any theta s or any sine theta s or cosine theta s. So let us see. So this is application number 1. Let's say, first of all, we take the example of some 3 balanced set of currents example. So we say this is IA, these are the instantaneous currents, IA, B, and C. So these are in the ABC frame. Okay, so IA, this is the peak value, IM, I peak cosine of omega st, then IB, this is IM cosine of 120 degree apart, and the IC is again further 120 degree apart. So these are balanced set of currents. We apply the Parks transformation. So what to do? You are looking for IDQ0 variables. So you have to take help of which one? You have to take help of TDQ0. Okay. So you are looking for DQ0 variables, and you already know ABC variables. So these are your ABC variables. So you put them in a vector notation or matrix notation, multiply that, sorry, pre-multiply that with the Parks transformation matrix, and you calculate the IDQ0. So that means if you complete this calculation part, that means you put K1 equals to 2 by 3, K2 equals to half here, and you bring these big matrix here, and then you cross multiply with this, you put the whole expression, okay, detailed expression of IA here, IB here, and IC here, take help of some trigonometric identity, and then you simplify your result. So you should get this. Okay, so again, you see, because of this balanced three-phase system in the ABC frame, you should get 0 for the I0 component in the DQ0 frame. That's why we can drop it. Okay, we can drop it, and we can only live with ID and IQ variables. So we see that, well, after transformation, we have this cosine omega st minus theta s, and again sine omega st minus theta s. But we claimed that, well, we will get rid of the cosine and sine, right? But still we have this. Any comment on this? What is this inside this cosine? Okay, let's go back again to our previous figure. We have to again come here. Okay, so this is your theta s. Okay, what was delta? What was delta in the swing equation? Probably I have to open the swing equation slide. Let us try to open it. Let us try to relate what I'm trying to say to you by sharing a new slide, which is the swing equation slide. So this was the swing equation slide, and the delta that I'm talking about is actually this. So you see, theta m, the theta s that we are mentioning now, okay, the theta s is basically this. Okay, this is our theta s, which is measured with respect to a stationary frame, which is for our case, which is actually the a-axis. Okay, and this rotor position, this is actually our d-axis, right? The d-axis direction actually represents our rotor position. So theta s is the rotor position measured from the a-axis reference or the stationary reference, whereas delta is, again, it is the rotor position, that is the d-axis position with respect to some rotating reference frame. And from this diagram, we established this, if you can recall. Okay, we established this relation between theta m and delta m. Well, for the time being, let's say it is theta s. So what is delta? What is delta m? It is theta m minus omega s into t, where t is the multiplied with the speed of the reference frame. Omega ms is the speed of the reference frame. Remember, speed of the reference frame. But because we are modeling the synchronous machine, we took the speed of the reference frame, rotating reference frame, as the same as the same as the synchronous speed, omega s. So omega ms was set equal to omega ms. So this was our delta m. Okay, what was the difference between delta m and theta m? What benefit actually we were getting with the introduction of delta m?
time independent.
Yeah, delta M was time independent.
Time
So in the steady state, you see this frame, this rotor position, as long as it is moving at synchronous speed, this reference frame, it always rotates at synchronous speed. So this angle delta M will remain constant. So even the time is progressing, even time is increasing, even then this delta M will remain constant as long as your system is under steady state. So this was the advantage we were actually getting with the introduction of the concept of this synchronously rotating reference frame. So this delta M is actually theta M minus omega MST, right? Now remember this, keep this in your mind. So we go back to our original lecture that we were following, and that is this. Now look at this. What do we have here? Omega ST minus theta, okay? Omega ST minus theta. So what is this actually? If delta S,
Delta M.
It is.
see, this is delta S. So as long as your system is running at synchronous speed, what would happen to this cosine delta S? Will it be a constant?
Yes, sir.
Yes. So this is nothing but this block over here. This is nothing but delta S or delta M, whatever. This block is a fixed value, So because this will remain constant in a steady state, cosine of some constant will give you some other constant, right? Sine of some constant will give you some other constant. So all these will be constant in steady state. So this is, so you see, this is the benefit that we are actually looking for. So we started from some time dependent parameter, time dependent variables, okay, time dependent variables. But then we have come up with some other variables after Parkes transformation, which are actually not time dependent in steady state. So this is the benefit that we are getting, okay? And you see the peak value of IA in the ABC frame, IA or IB or IC, the peak value was IM. And because we are taking this combination of K1 and K2 here for representing this DQ0 matrix, so we end up with the same peak value. That was the benefit that we talked about earlier, mentioned earlier, that the peak value in the DQ0 reference frame and the peak value in the ABC reference frame, they will remain same. So this is the benefit that we will get with this set of K1 and K2. And the internal calculation, probably 1 or 2 or 3 lines, that is left to you, okay? Probably, inshallah, you will be able to do that at this stage of your study. In the postgraduate level, it is expected that you should be able to do that. So I will leave it to you. Now let's move forward. So this is what is actually done, okay? So we substitute theta equals to omega ST plus delta, okay? So this was the relation, actual relation. So delta would become theta minus omega ST. So you see theta minus omega ST. So the relation is actually reverse, okay? So that will be reverse. So cosine of this minus delta. So that means this internal thing is not actually delta, but it is minus delta, minus of delta. So cosine of minus delta is the same as cosine delta, whereas sine of minus delta is minus sine delta, okay? So that's why you end up with a minus sign over here. You get it? So this is the conclusion of the derivation or application of Parkes transformation for a balanced 3-phase set of currents. What is the magnitude of current? In this case, the magnitude of current, similarly, you have 2 components. The third component is actually 0. So you have 2 components, two components of the current in the DQ0 frame, one along the D axis, another one along the Q axis. So if you look for the magnitude, simply it would be square root of this ID squared plus IQ squared, okay? And the 0 component of current is 0. For voltage, in the same way, you can take a voltage example, 3 balanced set of components for the voltage phasor, VA, VB, and VC. You can represent them by the cosine omega t, then cosine omega t minus 120, cosine omega t plus 120. In the same manner, you can calculate the v dq0. Or if you have the values for vd, vq, and v0, then simply if you know the inverse matrix for the Parkes transformation, so in that case, you can also achieve the expressions for VA, VB, and VC. Similarly, for the flux linkage, you can use the same sort of relationship. Okay, if you know ABC frame reference, if ABC frame variables, you use the Parkes transformation matrix to get the DQ0 frame variables, and this is the reverse one. If you know the DQ0 flux linkage equations, you use the inverse of Parkes transformation, and you end up with the ABC frame variables. Now, for the apparent power, what is the expression for apparent power? With respect to instantaneous variables, what is apparent power? With respect to instantaneous variable, this is VA IA. No, not that one. This is three phase instantaneous VB IB plus VC IC. Okay. So all these are instantaneous, okay, function of time. Instantaneous means function of time. So if you want to write this expression in terms of vector multiplication, then you have to transpose one of them. So I'm transposing the voltage one, VA, VB, VC, transpose of this. That means they are actually aligned like this, VA, VB, and VC. This is your vector. And then IA, IB, IC, like along this, okay, IA, IB, and IC. So when you multiply them, you get this same expression over here. So if we continue with the calculation, for the apparent power, what to do? So you have the ABC reference frame variable. You want the S value in the DQ frame, the DQ0 frame. Okay. So how to do that? Let's proceed. So the VABC, you know the VABC, you want to go into the DQ0 frame. So what to do? Use this expression. So simply replace the VABC by this expression, T dq0 inverse VD VQ V0. Okay. So you see what we are doing. Simply we have a transpose. So T dq0 inverse is pre-multiplied with the VD VQ and V0 vector, and the whole is actually the transpose of that. Then you have IA, IB, IC. So similar, in the similar manner, you want to get you want to replace IA, IB, IC by the corresponding ID, IQ, and I0. So you have to pre-multiply that with the T dq0 inverse matrix. And then you cross multiply this thing. Okay, you just multiply this whole thing. You remove the brackets, open the brackets. So what do you get? You get this thing. This first part is simply the matrix transpose formula. Okay, if you have A, B, matrix A and matrix B transpose, then if you remove the bracket, then you get B transpose into A transpose. Okay, this is the matrix formula. So that is to say, if you have something like this, like AB transpose, AB whole transpose, if you want to remove the bracket, then you have to write it like B transpose into A transpose, and not A transpose multiplied by B transpose. This is not equal to A transpose multiplied by B transpose. Remember, they are not equal. Okay, so if you remove the bracket, if you open the bracket, expand it, then you will get B transpose into A transpose. So this is what we are getting. So this will come first, B transpose, and then this is the A transpose, and then there is no transpose. So simply you remove the bracket. So you have T dq0 inverse, and then ID, IQ, and I0. So now what do you have? You see there's a block intermediate. There are two blocks intermediate to this whole multiplication term. So you have T dq0 inverse transpose multiplied by T dq0 inverse. So what do you get? Anyone? Suppose you have B transpose into B. What do you get?
1.
1. Not 100% correct. Maybe partially I can say it's correct. It will only be 1 if the size of this B is 1 by 1, otherwise not.
Identity matrix.
Yeah, it would be identity matrix. Excellent. So, and the dimension of these identity matrix out of these would be what? Remember the dimension of TDQ0 inverse? What was the dimension?
3 by
3 by 3. So the identity matrix, after multiplying these two blocks, the identity matrix that you will get would be simply 1, 1, 1, and all other zeros. Okay. So when you try to solve this expression on your own, just use this relation instead of these two. In between, you have to write this identity matrix where the dimension of these identity matrix would be the same as the dimension of the parent matrices here. Okay. So then this 1, 1, 1, and remember, we besides this 1, 1, 1, actually in the representation of TDQ0, we had some constant multiplied, right? So because of this constant outside this DQ0 matrix, what we will get when we multiply this TDQ0 with this TDQ0 inverse, then the thing that you will get, there will be some effect of these constants, okay, K1 and K2. And because of that, you will not actually get exactly 1, 1, 1, rather you will get something else, okay? So this presence of 3 by 2, 3 by 2, and 3 should not be misleading. They are present here because of the constants used for representing the matrix themselves, okay? So you had K1 and K2, and depending on the nature of K1 and K2, the values of K1 and K2, these values would be affected, okay? But in general, for any other matrix where you don't have any constant being multiplied with the matrix, all of the matrix elements, in those cases, you expect to have an identity matrix. Okay, so do you get the point what I'm saying? Why they are 3 by 2, 3 by 2, and 3 instead of 1, 1, and 1?
Yes, sir.
Yeah, because of the presence of K1 and K2. Okay, because of those things, actually, when you cross multiply, when you just multiply these two matrices, then that will result something other than 1 along the diagonal. Okay, so when you complete the calculation, you should end up with this matrix, 3 by 3 matrix. And then you have these the pre-multiplication of VD, VQ, and V0 transpose, and post-multiplication with I, DQ, and 0. And then if you complete this calculation, these three multiplication of these three matrices here, when you complete this multiplication, then you end up with this 3 by 2. There is a 3 by 2 at the beginning, whereas the ABC frame representation is simply this VAIA plus VBIB plus VCIC. However, in the DQ0 frame, when you transform your power from ABC frame to DQ0 frame, then you see, well, there is some difference with the representation. In the DQ frame, you see there is a additional 2 multiplied with the 0 terms, and there is a 3 by 2 at the very beginning. Okay, so they actually don't look similar. Okay, their appearance are not identical. So this kind of transformation, is known as non-power invariant transformation. Okay, non-power invariant transformation means, for understanding that, we have to know what is actually power invariant transformation. So in power invariant transformation, what we will get or from where we will actually start, we have to start with a different set of K1 and K2. Okay, remember, we talked 2 different sets of K1 and K2. One set of K1 and K2 ended up with this expression of S and this relation between ABC apparent power, ABC frame apparent power, and DQ0 frame apparent power. Whereas if we start with this K1 and K2 for representing the TQ0 TDQ0 and TDQ0 inverse matrices, if you use these K1 and K2, then if you follow the same steps as I have shown here for calculating S, but with this K1 and K2, then you will see, well, now you see they look identical, right? VAIA plus VBIB plus VCIC is equals to VDID plus VQIQ plus V0I0. So because of their similarity in representation between these two frames, this is called power invariant transformation. So to get power invariant transformation using the Parkes transformation matrix, you have to take this set of K1 and K2. Okay. If you take the previous set of K1 and K2, then that is non-power invariant transformation. But with the previous choice of K1 and K2, what benefit we got? We got that, well, IM in the ABC frame was the same as IM, that is peak value of IM was the same as DQ0. That was with previous K1 and K2, okay, taken previously. This was the benefit. The disadvantage, that doesn't give you power invariant transformation. That ends up with non-power invariant transformation. Whereas with this set of choice over here, with this set of choice of K1 and K2, you end up, or you will end up with power invariant transformation. But in this case, you will not get this. So the peaks for the ABC current variables and the peaks for DQ0 current variables will not be identical. So it depends on you which choice you will follow and which suits you. Okay. If you want, you can go for power invariant transformation. If you want, you can go for non-power invariant transformation. It doesn't matter. Ultimately, you end up with whatever you desired. Okay, you desired to transform from ABC to DQ0. However, it looks quite good because you are writing in an identical manner. Okay, it looks good. So the power invariant transformation, you get identical representation. But intermediate steps in the IM calculation of IM, you don't get the same peak values. That's the disadvantage. So you can follow any of this. There is nothing special. If you want to keep your current calculation simple, then you go for the first choice of K1 and K2. If you want to keep your power calculation simple, then you stay with this choice of K1 and K2. Then we see another application of Parkes transformation. Now we are going into our topic of interest. Okay, we started from equation 1. Okay, remember we started from equation 1 for these slides. So now we are going to apply the Parkes transformation for our equations set 1a to 1c. What was that? Let's go back and check. So this was 1a and 1c. Okay, 1a, 1b, and 1c. Now, can you write them in matrix form? This whole thing. So if I want, I can write it in vector and matrix form like this: VA, VB, VC equal to what? Minus RS. Probably I have to write with some smaller fonts. We don't have much space. VA, VB, and VC. This is my vector representation for the ABC voltage. There is a minus. Then I have currents, IA, the current vector, IA, IB, and IC, plus d by dt. And I can actually expand these, right? Lambda A, lambda B, and lambda C. Well, for the time being, let's keep it as, lambda A, lambda B. These are the flux linkages for the 3 stator axis coils. Now, what should I write here? What should be the dimension of this matrix, this blank matrix?
3 by 3.
3 by 3, excellent. Now what should be the entries? I want this.
RS 0 0.
Yeah, so that will be a diagonal matrix. Okay. So simply if you fill up this diagonal matrix, then you will reach there. Okay. So this 1A, 1B, and 1C can easily be written in this form. Okay. VA, VB, VC, then a 3 by 3 matrix comprised of the diagonal elements RS, IA, IB multiplied by IABC plus D over DT, that's the differential operator. And that is operated on the flux linkages in ABC frame. So in the slide that is going to follow, you will not see this representation, rather you will see this representation. That's why I am writing it over here. So with this discussion of the model, let's go to that slide. Okay. So after that, actually what we have done, let me tell you. So actually few more lines are erased from and not written over here. There are some skipped steps. So let me write that part again for your convenience. Okay. So we started, actually this derivation was started from here. I'm not writing the zeros, okay, just to save my time. All the other entries for that matrix will be 0. This is IA, IB, IC, plus this will be D over DT, and then lambda A, B, C. Right? This is what we discussed just a few moments back. So this is our matrix. But all the elements there are in ABC frame, right? We want to apply Parkes transformation, and we want all these representation in DQ0 frame. So how may I replace this ABC? And how may I write it in terms of VDQ0? What should I do? I simply write TDQ0 inverse. They should be aligned. TDQ0 inverse multiplied by VD, VQ pre-multiplied. Okay, so the TDQ0 inverse should be pre-multiplied. So simply I'm replacing the expression of VABC with the corresponding expression of DQ0 with the help of the inverse Parkes transformation. Okay, so the left hand side over here can be replaced by this, right? Next we have the equal sign. So for the time being, this will come. I will tell from where it is coming. So look at this RS diagonal element. So this is this matrix. Then again, this TDQ0 pre-multiplied with IDIQ I0. This block, what is this block? What is this?
IBIC.
Excellent. So that is this. Okay. So that is replaced again with the help of TDQ0 inverse IDIQ I0 plus you have a D over DT lambda ABC. Now you see there is an additional operation, differential operation. So this lambda ABC and this is the corresponding DQ0, right? Inside the bracket. Then outside of this bracket we have D over DT. So this is your D over DT. Up to this is understood?
Yes, sir.
Should be. So what is left? So you see there is another pre-multiplication of TDQ0. That TDQ0 is actually coming from here. Okay, because when you see when we are replacing this, we have an inverse, a pre-multiplied inverse Parkes transformation, right? And what we are writing, we are only writing here VD, VQ, V0. So actually this was there. This was there. And this was the thing. Okay. So we are actually taking this pre-multiplied TDQ0 inverse to the other side of the equal sign. and then it becomes T dq0 only. You get it? There are some steps intermediate. So these are the, in short, what we are doing. We are replacing everything here. Everything in this equation, we are replacing by the corresponding dq0 variables and the required Parkes transformation or inverse Parkes transformation matrices. And then I'm writing another line just after that, after the transformation, I'm writing another line by taking this pre-multiplied T dq0, which was here, somewhere here, and I'm taking it to the other side. Okay. So it is becoming T dq0. Nothing, there's nothing, no magic. So after taking it to the other side, we have a very complex relation. Okay, very complex relation, which requires actually several pages of lengthy calculations, which is not shown, of course, here. Okay, which is not shown in these slides. But not all of these parts are actually lengthy. Okay, why? Let us see. Not all the parts are lengthy calculations. What is this? These first three terms. Can anyone tell what is the shortcut for this matrix multiplication? So in between you have a diagonal matrix. That is the most important thing. Okay, symmetric, any symmetric matrix will also do. So a diagonal matrix is the example of a symmetric matrix. Symmetric matrix means that the that all the off diagonal elements are equal, whereas the diagonal elements one special case of symmetric matrix, where that all the diagonal elements itself, or the diagonal elements themselves, are equal, and the off diagonal elements are also equal, but they are equal to 0. So this is one special case of symmetric, positive symmetric matrix, or it should not be called positive, it is semi-positive, because these are zeros, not exactly positive. So this is semi-positive, semi-positive definite matrix. Okay. So if you pre-multiply a semi-positive definite matrix or any symmetric matrix by some other matrix, and if you post-multiply by the inverse of the first matrix, then the resultant is simply the intermediate matrix itself, or the symmetric matrix itself. Okay, this is the shortcut formula for these matrix multiplication for these three blocks: block 1, block 2, and block 3. So there is no detailed calculation required. Okay, for getting this from here to here, it's not a detailed calculation, it is the shortened formula, matrix multiplication formula. The condition is that the middle block should be symmetric, should be a symmetric matrix, and at two ends you should have this matrix and the inverse of that. Okay. Okay, so you reach here, and then we have IDIQ I0. So this is IDIQ I0. But then you see we have one interesting thing remaining.
UV formula.
One interesting combination of different matrices. What is that? Rahid, please turn
UV
off.
formula.
Huh? UV. Yeah.
UV formula.
Yeah. This is UV formula. Thank you. So simply this is UV formula. Why we have to apply UV formula? Because you see, whatever terms we have, whatever matrices we have inside this d over dt term, both of them are actually function of time. Okay, both of them are actually function of time. This t dq0 inverse, it is a variable, you see, because of the presence of cosine theta terms. Okay, cosine theta terms. So it's not a constant matrix. Lambda d, lambda q, lambda 0. These are also flux linkage expressions. Okay, these are not again constants. So that's why you have to apply UV formula for differentiation. So T dq0 is the pre-multiplied matrix over here, and the same thing comes here. And then you take this first, lambda d, lambda q, lambda 0, then d by dt of u plus T dq0 is this one. Then you have v, or u d by dt of v, all the same. Okay, so this is UV formula. And then this part, actually this part, the calculation of this part is actually a bit lengthy. D by dt, t dq0 inverse. That means what? You have to calculate the time derivative of t dq0 inverse matrix. Okay. Then you have to multiply that with lambda d, lambda q, lambda 0, or you can change the orders also. Then you have to multiply that d by dt of t dq0 inverse with t dq0 itself. And then you can keep this lambda d, lambda q, lambda 0 at the end. However, these two will give you identity matrix, t dq0 multiplied by t dq0 inverse. That will give you identity matrix. So there is no problem. There's not a big deal. And you are left with d by dt, lambda d, lambda q, lambda 0. That's easy. That's easy. The only painful or painstaking thing is this part. So try it at your homes. Okay, you have to try it and submit this along with your assignment number 1. Okay, clear? So your assignment is simply, you just simply take this part and try to reach here and show the detailed calculation. So from where do you start? You start from simply this derivative, d by dt, t dq0 inverse. And then you multiply that, whatever you get, you multiply that with t dq0. And then you leave with, you still have these lambda d, lambda q, lambda 0. So while doing the calculation, you have to use some trigonometric identities very intelligently. Otherwise, you will never reach here. Remember, you have to use some trigonometric identities very intelligently. So once you use those trigonometric identities, only then you end up with these simplified expressions. Okay. So let me help you out. Why? Because you see there is omega, presence of omega in the final expression. From where actually this omega may come? Let me tell you. Let me give you some hints for the last few lines. So the hint is, if you look at the t dq0 inverse matrix, we don't have much time, probably 7 minutes left. Okay, not take long. Okay, so this is your t dq0 inverse, right? So when you take the time derivative of this, what do you get? What is the time derivative of this?
Sine.
minus sign.
Okay, so one of you said sine, one of you said minus sine. So it should be minus sign, okay? It should be minus sign. But is it enough? What about the theta itself? Remember, we are differentiating cosine of theta. So cosine of theta will give you, of course, sine of theta. But isn't theta s itself a function of time, as we discussed? Isn't theta s a function of time itself?
Yes. Yes.
So you can't stop here with the differentiation. You have to go up to the chain rule. You have to apply this chain rule and you have to end up with this. Do you get this point? Why we have to do this? First, what we are doing, simply chain rule. We are differentiating this cosine of theta s with respect to time. So that is actually, it is not an explicit function of time, right? It is not an explicit function of time. So what we are actually doing, we are splitting it like this. D cosine theta s. We are applying the chain rule of theta s dot d theta s over dt. That's what we are doing simply. You get it now? This is another way of explaining it. Because theta, cosine theta is not an explicit function of time. So what we have to do, we have to apply chain rule. And what is that? You simply take the derivative of cosine theta s with respect to theta s itself. And then your original differentiation is with respect to time. So you introduce one intermediate variable, differentiation variable, and that is the theta s. So you have to again differentiate this theta s with respect to the original dt. original variable. So this thing, when you calculate, you end up with this. And this d theta is over dt. What is this? What is the physical parameter for this?
Omega.
This is omega. So this is where actually from, this is actually the source of omega. Okay, this is actually the source of omega. This is omega. That's why you will find the presence of the omega in your final matrix representation. Okay. So this is only I have shown for one of the elements. Similarly, for all these elements, you have to do it, and it will take some pages, of course. And that's why it is your assignment. Okay. So go through the assignment and submit it along with whatever assignment I have posted. Probably I will update it with this calculation as the part 2 of your assignment 1. Okay, part 2 of your assignment number 1. So let me repeat what you have to do. You have to simply complete this calculation. You have to simply calculate this calculation, and you have to end up with this 3×3 matrix where you see only omega is there, nothing is special, nothing is there, no sine theta, no cosine theta, nothing else, no 3/2, nothing else, simply a minus omega is there, a plus omega is there, and for the 0 component, these are zeros, they will not appear actually. So we will stop today here. Inshallah, in the next class we will continue from the next slide. Okay, so is the assignment clear? Assignment part 2 for the first assignment. Simply you have to complete this calculation along with whatever I asked for in the assignment that I already posted. So I will update it, inshallah, and you have to submit both of them together as assignment number 1. So these are the calculation steps associated with the stator winding voltage equation. So once we follow these steps, then we will end up with this VD, VQ, and V0. That means the voltage, stator winding voltages will be no more in the ABC frame. Rather, these are the projections of the ABC voltages on the DQ and 0 axis. Okay, these are the projections. And for finding out the projections, we are simply using the Parkes and inverse Parkes transformation matrices. Okay, any question? We are not going to proceed any further because the time is almost finished. Okay, so if you don't have any question, then inshallah we again meet on next coming Friday. Okay, until then, assalamu alaikum.
Assalamu alaikum.
Wa alaikum assalam.